We're going to have a discussion here on layering. When we were talking about the decomposition of systems into separate components, I used the word component to mean any sort of division of the system. And in this case, we're going to take a look at ways that we can divide the system up into different layers. If I look at a set of abstractions, and they each represent a set of services or things that that layer can do, we can organize these layers in a way such that each layer is only dependent on the layer below it. So for example, if I were to look at layer A down here, that could be considered a layer that has the most basic services available. And we do this in operating systems all the time. At the lowest layer is the set of operations for very basic operating system behaviors such as time, security, files, or input and output. The next layer up, we might have the file system and related type services. And then the layer above that, more complex operations that allow us to have terminal sessions, that kind of thing. And at each point, you can see that all of these are only dependent on the layer below it. This is very useful because each layer is only dependent on the one below it, which means if the one above it changes, the one below it doesn't change. And what this does is it reduces the coupling in the system. Layer D is only coupled to layer C is only coupled to layer B, and layer B is only coupled to layer A. You don't see very many dependencies that reach down like this. Now, the reason you don't want that to happen is if layer A changes, then all of the abstractions above it are bypassed, and layer D is completely dependent on this very low-level set of abstractions. In this diagram, I also have a situation where layer E is dependent on layer C, and in this case, these two are at the same level. In other words, they're at the same sort of level in the hierarchy. And there, we have partitioned the system side to side as opposed to up and down. By side to side, we mean they're both dependent on the same level or the same layer below it. Now, this process of layering allows us to introduce especially the ability to decouple layers above it from dependencies below it, such as hardware dependencies or operating system dependencies. So, for example, if layer A hides most of the hardware dependencies in a system, then layers B, C, and D can all operate independently. We see this in the Unix operating system where there are very few hardware dependencies, and those that are hidden mostly in the C language on which the rest of the system is based. In the case of layers D and E, there we have side-to-side partitioning, and in this case, what we've done is we've broken the system into different areas of interest, but they're basically at the same level of abstraction, meaning at the same scale. Now they both depend on C, which is fine. C hides some layers of some levels of detail below it and creates a common set of services. Those services represent things that the layer supports and provides through an interface. Finally, it's worth mentioning that each layer can have multiple clients above it, but they never reach beyond the layer that's immediately below them. So layer D and E are two of the multiple clients of layer C, and layer C is dependent only on layer B. The other thing that's important to note here is that layer C has no dependencies back to layer D and E. Likewise, B has no dependency up to C, and layer A has no dependency up to layer B. So this direction of the dependency is important, and then the vertical versus the side to side. Side to side is a way of partitioning out responsibilities at the same level of abstraction. The stacking up of the layers allows me to have a series of usually more successively refined layers, abstracting out lower levels of detail.